Hello, today's lesson is the exponential function. This is one of the most important functions that you will be facing um, uh, both in high school and university. This function has many properties, many features that we'll be talking about later, especially in real life applications. So first, let's talk about how this function looks like. Now, the exponential function general formula is f of x is equal to a to the power of x, where a is the base of the function and x is the exponent. Okay, here there is a condition for this to work. A, which is the base, must be, here I'm going to write it here, a must be greater than 0. Okay, now in this case we're going to have two cases from this. Okay, we have when a is between the 0 and the 1. We will see how our function is going to look like. And in the other case, when a is actually greater than 1. Now, in the first case, for example, f of x is equal to, we said it's a here, our function, which is f of x, is equal to a to the power of x. Okay, so when a is between 0 and 1, that means we're talking about decimal numbers. If it has a decimal number, if the base is decimal number, now by common sense, a decimal number is up to a certain power. What will happen to this number? The number itself will be increasing, but what we'll be having is the value of this number is decreasing. I mean, the number of digits will be increasing, but the value is decreasing. So this will result in, this is an example, f of x is equal to 0.5 to the power of x. Now here, x is our input in the function and the output is f of x, which is a to the power of x. Now here we're going to talk about the behavior of the function. First, let me graph it for you, and then we'll talk about the behavior of this function. Okay. So this is y, this is x. The exponential function in this case is going to look like this. Okay. Now here, again, we're talking about common sense. At the point when a is equal to here, let's say, okay, here we already have a, we already have our function graphed for the changing values of x, which represents the domain. That's something we're going to talk about later on too. So here for the behavior of this function, as x is increasing, so which means as x is approaching infinity, what will happen to f of x? Here, look, when x values are increasing, what's happening to the y? It actually approaches or heads to 0. Okay, what about as x is approaching negative infinity, or what we call it as x decreases? What happened to f of x in here? F of x heads infinity, because look, it's going up when x is decreasing. Now this only happens when we have a is between 0 and 1, so when a is a decimal number, when the base is decimal number. Okay, this function is strictly decreasing, so because look what's happening here. At some point, this is the f of x that we had, and then it just decreases very fast. So it's called strictly decreasing function. In the other case, where a is greater than 1, what we will be having here is as, okay, let me just first put let's start with the example, which is f of x equals to 2 to the power of x. So instead of having half in here or 0.5 in here, which is a decimal, we're having 2. When we graph this, we will get this function. It's like a mirror to the previous one. Okay, this is y here, this is x here, and this is our f of x in this case. Now, okay, let's write this first. Let's start with the end behavior of this function. As x increasing or increases, what happens to f of x? Now here, f of x is also increasing, or also heads to infinity, or also approaching infinity. And the other part of the end behavior is as x approaches negative infinity, or we can say as x is decreasing, f of x is heading or heads to the 0. So it's the exact opposite of this one, even though we're still talking about the same function, but in two different cases. Okay, which is strictly increasing in this point, because look at this. If we're talking about finding slopes at certain points, which we called it before finding a derivative of a function, you will see that every single slope in here represents a slope that is positive, but in here it's always a negative slope, which means this represents a decreasing function, and this is an increasing one. Okay, now in general, we have some general points that we'll be talking about, which is this function is always greater than 0. It never crosses the x-axis, never crosses the x-axis, no matter what. It always intersects the y-axis at y equals 1, which is right here. Do you know why? Because if we think about it, no matter what a is, when x is 0, it's going to give us 1. So at the point that is x is equal to 0, it will be always, the f of x is always 1, because the power is 0, and anything that has a power of 0 gives a value of 1. So it always crosses the coordinate 0 and 1. Now at x equals 1, which is the other way, which is one of the most important points in here. Let me just write it here. We said f of x is equal to a to the power of x. That's the general form of an exponential function. Now, if a is equal to, sorry, what did we say before? No, when x, sorry, we're talking about x now. When x is equal to 1, this gives us the same amount or the same value of the base, which is a. That's why when we're going to use this function in the differentiation and integration, it will give us something different, something that we didn't go across before. We will see it right now. Okay, before we talk about that, let's talk about something called the natural exponential function, which is what you will be using a lot. The natural exponential function. The natural exponential function is, instead of having f of x that is equal to a to the power of x, we will be having e to the power of x, where e is a number that is equal to 2.718 and it has about a million approximate or accurate, actually it's not approximate, a million or more accurate number that was found, because it has a certain formula for this, and this and the details about this number will be given to you later on. Anyway, this is called, it's written E, now this number is called EULERS, and it's pronounced Euler's number. So using Euler's number gives us one of the most accurate function used in our daily life and in some real life applications. The function e to the power of x is something very known and something that actually doesn't change, because the base here is just constant, which is, it always looks like this. It's an extremely decreasing function, and this function has some properties. The value is very important because it creates useful properties. That's why it's actually used. And this value was found from it's like a limit of a formula that is 1 plus 1 over n to the power of n. If you put this in the calculator, the more numbers you put here, the more accurate this you will get into this number. Like, just put any number in your calculators and let me know what you guys found. The first number that you can start with is 1, and basically here when we get 1, when we put 1 and 1, you'll get 2 without any decimals next to it, or any fractions or any decimals. But when you increase the amount, when you increase the value of n, you will get more accurate into it, until you reach thousands and thousands of numbers. So this has like millions to approach this number. That's why it's not called a formula of E, it's called the limit of the formula of E. So anyway, let's talk about the important properties of this E, or this Euler's number. The important properties are, number one, at any point at any point of this function, the slope is equal to the value of the x itself. So for example, if we took this point and we tried to find the slope of this point, when you find the slope at this point, you will get the slope that is equal to ex itself. How? For example, at x equals 0, the value of ex is 1, because it's e to the power of 0, which is equal to 1. The slope in this case, at x equals 0, you will get a slope of ex, which is 1, so you'll get a slope of 1. Another example, if x is equal to 1, the value of ex is ex itself, or e to the power of 1, and the slope also will be e. That's why when you're going to use e, which is the Euler number, in differentiation, you will get ex itself, so the differentiation of ex is ex. Also, this leads us to the second property of it, which is one of the most important properties as well, which is the area under this curve. The area under this curve at any point gives you exactly the same amount of ex again, which means the integration of ex is ex itself. Okay, so this shows us okay, so now we just illustrated the most important properties that makes using exponential functions useful with the Euler number. send me your questions for this video, because starting from now we'll be using a lot of exponential functions, and we're going to go back into differentiation and integration, but this time we're using this additional function. Contact me for any questions, and please check the assignment in Google Classroom.